we're talking about, I abbreviated the theme with CG. I mean, that's a stupid abbreviation. So, compact, I don't know about the order, classical group. I'd like to speak about these groups. No problem?
No,
Or you
just
I would like to speak about these groups, and these are the groups that, for example, Hamlin Weil looked very carefully at in the early days, and others. Toward the beginning of the 20th century, so this is a rather, for me, rather new subject compared to what we talked about. And the beginning point this morning, so this morning we began with an example, just to remind you, of a certain thing which I called M, and this word M is now, I'm going to use the word manifold for this thing, is the sphere. And to get the numbers correct, I'm going to talk about the n-1 dimensional sphere. And the reason I call it n-1 dimensional sphere, I want to look at it in Rn. Right, and so Sn minus 1 is a set of vectors in Rn with norm 1 and with the standard norm 1. And then we look at the stabilizer. Well, we looked at the appropriate geometry. The geometry is defined by the norm. Which really means the geometry is defined by the standard inner product, which is the same thing as the norm. And the standard inner product is, say, VW is in brackets V1, W1 to Vn, W. That's what we talked about this morning, the usual sphere. And I drew a picture this morning of S2, but so there's a metaphorical picture here of the sphere Sn minus 1. And here is 0, and this is a radius 1. And we're interested in the group, and in the end this is going to be a compact group, so I'll call it K at first. There's a set of transformations, linear, so I'm interested in the linear transformation. So T in GL, in this case n plus 1 R, which preserve the inner product. So I'll write it down in a sort of elementary way. It preserves the inner product. Standard inner product. And of course, we were using the standard basis. If you have such an operator, we have a matrix of that operator. The matrix of the operator in the standard basis, the way you think of it in any basis, it's a matrix that looks like this, and the first column is the column vector of E1, the second column is the column vector of E2, the standard basis E1 through N, and the last column is, now how many do we have here? We are in Rn plus 1, so n plus 1. Okay, and the condition is that the operator is in K, if and only if this basis T of E1 through T of En is an orthonormal basis. That we show. Yes.
Is this now over the complex numbers? Because
No, this is
that's
over the
a-
real numbers now.
and
I will
this-
go over the complex
in the
numbers.
dimension of the spheres, then.
Oh, I got
Because
ahead of myself, I put a 2 here.
yeah.
Yeah. For some reason I put a 2 here, and the reason was what you're thinking about. And I will come to that in just a minute, okay? I'm sorry, yeah. So, I don't know why I did that, I guess I'm a complex. So, and this morning we talked about the 2 sphere in great detail. So we prove this, and this is an equation. The equation that this is T transpose T is equal to the identity. That's the equation. If you don't believe me, write down T and T transpose and multiply it out, and that will be precisely the condition that this is orthonormal basis. Right. Yes. And let's see why that really is the equation. By the way, many people would say that's a huge number of equations. In some sense, right? Right, because it's an equation of matrices or operators. So that's an equation for each thing. Right. So why should that be the equation? Well, the reason is if you have a vector v and a vector w in the usual way, the standard inner product is just v transpose w. I'm thinking of these things as column vectors. And then if you put in T of V, T of W, I've mentioned this to you before, but I'm just reviewing this. This becomes V transpose, T transpose, T W, and that has to equal V transpose W. So this is the statement that T transpose T equals the identity. Okay. So just for fun, let's do it in the 2x2 case, just for fun. Why not? It doesn't hurt, right? So let's see here. If T, the matrix of T, I'm really talking about the matrix of T. So the matrix of T, say, is A, B, C, D. Then the matrix of T transpose is A, B, C, D. And now you multiply it out, so let's multiply it out, A, B, C, D. Yeah, that's the transpose, I hope. I have to put that up there. Yeah, I have to, yeah, I did it right. That's the transpose, and now just put in A, C, B, D. And just for fun, let's multiply this out. This is going to be a multiple. That's interesting, A squared plus B squared. You get a lot of knowledge by just doing some calculation of matrices. A, C, B, and then of course, same thing, A, C, B, D here. And now C squared plus D squared. And that's T times T, in matrix level, T transpose. And you see this, the equation is, that has to be the identity. And so that says that this norm is 1, this norm is 1, and these things are orthogonal. Right? So it's nice. Okay? So that's the condition for being in O2, and in ON it's the same thing. And this morning I showed that ON, well, I'm going to say it more precisely. So this is just for fun, n plus 1, because, do I get it right with the n's and n plus 1? Oh, k. K, which in this case is on plus 1. That's what we're talking about here, is embedded, because we just saw what it is. All you need to know that these things are length 1, so that is a sphere. What is this? This is a vector in Rn plus 1, so this is in the sphere, n-dimensional sphere in n plus 1. This is in the n-dimensional sphere in n plus 1. This is an n-dimensional sphere in n plus 1, so the column, just putting these columns in the sphere, you get this embedding. And of course, we have the addition, so what is the statement is that the matrix of T gets mapped to T of E1 to T of En, and that is a certain set, a certain closed set in the sphere, because it has to satisfy the condition T of Ei is perpendicular to T of Ej, for I not equal to j. And those are the equations which define the orthogonal group in a product of sphere. It's very interesting, right? It's not so obvious what that looks like in a sphere. You have all these spheres. You have inside that sphere that interesting orthogonal group. And these are beautiful equations. And we say quite often that then K is a compact submanifold, because these equations define this in a very smooth way. So we call it a submanifold. The product of spheres. Very interesting. So that is, in some sense, the first classical group that you meet is that orthogonal group. And quite often, and the physicists will tell you this, that, and we've seen it already with O2, because in the case of the Euclidean group of special interest, is SO, in this case, n plus 1. Well, I'll just write SON here, it doesn't matter, I mean SON. And this word S means by definition, that the determinant of this operator is 1. Now, that is the letter S means that. Okay. Now it's not there just for fun. It's there for a real reason. Because if you start with a parallelogram, multi-dimensional parallelogram, there's some fancy words for this. The German word I mentioned earlier is Spat, and I like that. It's short. It's only four letters. In English, it's parallelepiped, and I've never understood that word. So the German word is much nicer. It's Spat. What that means is, well, I mean, what is this? Here, for example, here's one with a vector v1, a vector v2, and that's a two-dimensional parallelogram because you can just fill it out and get a parallelogram. And so a parallelogram in general, so the general Spaten parallelogram defined by n vectors, which are independent, is the object that you get by taking the convex hull of those vectors. Right? So this is the convex hull of this thing. So this is the generalized parallelogram. And then you're doing Euclidean geometry in n-dimensional space. This is n-dimensional space, so you have the Schwatt in n-dimensional space. These are n independent vectors in n-dimensional space. It's a basic, but we're thinking of a geometry in Rn. So that's a generalized parallelogram. For example, in R3, I probably won't draw it because I messed this up, but it might look like that, right? And then you take the convex hull, so it's the interior, of course, included. So taking the convex hull. And in the standard, geometry of the plane of Rn, the area of this spot, which most people wouldn't call, say, area because you're thinking it's very high dimensional, so maybe the word you would prefer to use is volume of the spot. So maybe I'll even be more precise, the n-dimensional volume of the spot. Of course, is simply the determinant of those vectors. That is the area or volume of that spot. Okay. Now, there's somehow a non-trivial fact here. If you take now a linear transformation T, and you take T at the spot and move it, this generalized parallelogram, you move it with the transformation. You can imagine you're going to be rotating this thing out and dilating this thing, doing all sorts of terrible things. So it's not going to be a symmetry of this thing. Yeah? It's an obvious thing that you have. The spot that you get here is T of V1 through T of Vn. I mean, that's absolutely, that's just a definition. You move the vectors and so on, right? So it says that the volume of T of the spot is equal to the volume of T. The spot defined is the volume of Ts, which is equal to the determinant of Ts, which is equal to the product of the determinants So what we have shown here is the volume of, if you hit it with this linear transformation, the spot is the determinant of the linear transformation of T times the volume of the spot. So it says that volume changes by the determinant when you operate. So that's the meaning of the determinant. By the way, that's the definition in my mind of the determinant. The determinant is the volume of that spot in the standard Euclidean geometry. So finally, why did I say all of this? So if you have a linear group G and GLN, then you are looking at S of G. These are the G, the G, so that the determinant in G, so the determinant is equal to 1. what you've imposed here is these are the volume preserving transformations in in G. So that is the reason quite often we go to SO, SU, SP, SL, SS. No, I don't mean that in a nasty way. Yes, yes, yes. And we say the special linear groups. Special means, it's not special, it means simply that volume is preserved. And that's an interesting thing because we're talking about symmetry here, so that means volume is partially one of the things we're interested in being preserved. Okay. Yes.
Is SON also a compact submanifold or?
So So we have ON. Of course, like your questions, very nice. We have ON, and let's just be sure we understand a little bit of the details. Let's even look at O2. We've already maybe O3. Okay, we talked about O2 already. Let's talk about O3. O3 contains, of course, SO3. By the way, SO3 is a very important group in physics. SO3. And now we want to see what is the difference. What you asked is it a submanifold and so on, what is the difference? So let's see if we can make something, some operator which is determinate look at this operator. It is usually a stupid operator like that, right? You just write down, and this is an operator with determinant 1, minus 1, right? Okay, so that's a very interesting thing. So this thing generates a group of order 2. In O3, right? I mean, you multiply it by itself, right? That's it. Let's look at some other things. Look at this one. That's also in O3, right? Because that's an orthonormal basis, right? And that's determinant -1. This is also a group of order 2 in O3. I like this group much better. You know why I like this group a lot better? Because this is minus the identity, right? And it commutes with everything. So I like it a lot better. Okay? So, yeah. So look at this. Look, it commutes with everything. This is really good. If I write O3 down, I say, well, this is what you asked me about SO3, what's in there. So I'm not finished with this equality, right? This generates a group of order, so it generates a group of order 2, so I'll call it a C2, cyclic group of order 2, right? And of course, that I think is completely clear, and it commutes with everything, so this is wonderful. I don't even have a semi-direct product here, I have a product, because it commutes with everything, right? That's wonderful. That says O3 is equal to SO3 times this cyclic group of order 2. So O3 is here, SO3 is here, and here is the identity in SO3, and here's minus the identity, and here's minus the identity, this is minus the identity times SO3. And it says, of course, altogether, this stuff here is O3. Because I have everything, I have everything. I was very lucky here. And so I answer your question by saying it is a component. In this case, SO3 is a component, or maybe that's not even connected, I don't know. It's a component, or several components, who knows? Yeah, so it's really connected. Maybe not connected, but it's much better than a submanifold. Yeah, maybe it's not connected, I didn't claim that. So, right, this is a problem. These groups sometimes are not connected. Okay. But it's a number, maybe it's not connected, but it's a number of components. And to get O3, you have to multiply all those things by minus the identity to get everything. So the answer to your question in this case is very simple. It's just some components. Okay? Right? That is always true, what I just said, for every one of these examples. Okay? And it's always this fact. Sometimes you just have something that has determined negative, and that generates a small thing, and there's no problem. So that's the story with the orthogonal groups. Be a little bit better in my didactics. And now, these are orthogonal groups, for the obvious reason. ON. And let me do mentally the calculation just so you can check. I told you this morning how to check how big these things are. ON. Let me see. OM. So is yes. So it's, I think it's n times n minus 1 over 2. And let me check what O2 is. O2 is one-dimensional, right? It's just a circle. And I would say I would say O2 is 0 dimensional. No, O2, no, that's correct. O2 is 2 times 2 minus 1 over 2, that's 1. Yeah, so this checks it. So I told you this morning a nice recursion formula for figuring this stuff out by the action on this field. Okay, now Mr. Weiss pointed out that I have complex analysis in my head. So, I will start now, this is the orthogonal groups, and now I will start discussing the unitary groups. And these groups are called UN. I talked about them this morning, but right toward the end of the lecture, so I want to repeat a little bit in case you were tired this morning. The model for me is, see, I never start with a group, I start with where it acts. So the model for me is what Mr. Weiss was pointing out I had in my head, is here we go to the 2n minus 1 dimensional sphere in Cn. Okay? So, So these are the vectors, so at this sphere, the same thing. But I'm going to very carefully write this over the complex numbers. Instead of z in Cn, Cn, I hope I got n, yeah, it's okay, Cn, such that norm of z in the standard norm, the norm of z is 1. and there's a convenient way to write that in the inner product, the complex inner product, I wrote it here. The complex inner product, the standard inner product between complex vectors is Z1, W1 bar plus, and so on, Zn, Wn bar. This is the standard inner product. And really, over the real structure, if you make the usual identification, Z alpha equals X alpha plus I Y alpha, that's the identification of Zn identified with R2n, then this thing is nothing other than just X1. What is it? Let's see, X1, so let's see, let's do it out. X1 plus square root of minus 1 yeah, we have to say what is, sorry. So here's the Z alpha, and then W alpha, say, is C alpha plus I eta alpha. And to get this right then, so Z alpha times W alpha bar is, I hope, what is this? This is X alpha, C alpha, alpha plus Y alpha, eta alpha, right? So that's the real part, and then the imaginary part is very interesting. So the imaginary part is, what do we get here? I times Y alpha, so Y alpha, C alpha, plus X alpha, eta alpha. Okay. So that's the inner product associated to the norm, and of course then the norm of Z is just the sum of Z alpha bar, and that is nothing other than just the usual norm, x1 squared. So x, oh, I shouldn't do that, yeah, so x alpha squared plus x alpha, x1 squared to xn squared plus y1 squared plus yn squared. So it's the usual, this is the usual norm, and so this is the usual real norm of this thing. Yeah, so this is really just the norm preserving transformations. I'm interested in this. So the two possibilities here. One, to keep the complex structure. So what that means is, what I mean by that is, I want to make sure I don't mess up the blackboard here. Keep the complex structure. I want to consider the transformations T, I want to consider K to be the transformations in GLNC, the linear transformations. See, that means it's complex linear. I'm keeping the complex structure such that norm is preserved. Norm is preserved. Standard norm is preserved for all V. That's one thing to do. And I, as a complex analyst, and almost everybody in physics is interested in complex linear transformation. I think that's true, Deepak, is that right? Complex linear transformation. Yes. We're interested in complex linear transformation, not. Or one thing to do, or don't forget, don't keep it. don't keep the complex structure. And so you look at K to be equal to P in GL 2NR in the real linear transformations, which is acting on Cn, which stabilize this norm. You agree there are two things to do. You either look at the complex linear transformations or the real linear transformations. Now, every complex linear transformation is a real linear transformation, right? So, let's call this K preserving the complex stuff, and let's call this K preserving the real stuff. It's completely obvious that K preserving the complex stuff is contained in K preserving the real stuff, right? Because the complex linear transformations are real linear. Okay, let's study that. Well, the real linear transformations that preserve that, that's a stupid thing. We just talked about it. Right? We just talked about it. That's the orthogonal group. So KR, the stuff that preserves the real structure, you forgot the complex structure. What do you care about the complex structure? I care, but you don't care. KR is just the orthogonal group. Now we have to see what orthogonal group that is. Well, orthogonal group 2n, R. Yeah? I mean, that's what we just talked about, right? Okay. And this contains KC, which is obviously much smaller because this requires that the transformation is complex linear. Yeah? So in fact, KC is the set of elements T in O2NR such that T preserved is complex linear. Okay? Yeah.
Does the fact that it is smaller than the other group come only from the fact that we're talking about the general linear group over the complex numbers?
That's right.
Or also from the norm? Or does the norm?
No, the norm's a norm, actually.
Okay.
It's because that's what I try to motivate. Well, I did a bad job motivating. I mean, you may write the norm down in a complex notation, but if you write it in real notation, it's the usual norm.
It's the same. Okay.
That's what you need to keep in mind. It's the usual norm. And that means your complex linear transformations here are going to preserve the usual norm, but they have the additional condition that they're complex linear. Okay? This kind of thing is true for any field. I mean, you have a small, right? It's completely obvious. It's a question of how the one field lies in the other. Yeah. So we're interested in this thing, and so we try to write this down. We have to ask the question: what is the equation which defines KC, and right now I'm going to call this something. This is going to be called UN, and this is the nth unitary group. So the question is, what defines KC in KR? You should always ask, what is the equation? Right? It's a subset, and if it's just some Mickey Mouse subset, you don't care about it, right? I mean, but it's got to be defined by some equation, right? And the equation is you'd have a real transformation and it should become complex linear. Okay. So in other words, what equation does a real linear transformation satisfy if it is to be complex linear? All of these things, all of you in this room can easily simply ask these questions. And, well, I need to put a question mark up there. Question mark. And now here it is. So, what is the condition that T is complex linear? The condition is that if you take a complex number lambda, a complex number, and multiply a vector by it, it has to come out. Right? That means complex linear. Is it not true? That's enough. Because it's real linear. Well, lambda equals A plus, lambda equals, say, A plus IB. And these are real numbers. So T of A plus IBV. Now this thing is real linear, so this comes out A T of V plus B T of IB. Right? That's the best you can say for a real transformation, because A and B are real. Right? So what you need, of course, is T of IV equals I T of V. That is a statement that the real linear transformation is complex linear. Right? 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 Okay, so let's look what that says. That says if we have a standard basis, maybe let's take a basis E1 of the real space, En, and this next basis is IE1 through IEN. This is a basis. This is a basis of the real vector space. And in that basis, the matrix of multiplication by I in the standard basis, the standard setup is really stupid, because you take here we go. We have to find out what the first column does, where did it go, what the second thing, and so on, up to the nth, up to the En, and then you have to figure out what happens to the next thing, IE1, and then all the way up to T of IEN. Yeah. So T of E1 is a lot of zeros because it's I times E1. So it goes down here and it looks like 1 and then 0, 0 here. And then T of E2, a lot of zeros, even more. The 0 here, and then there's a 1 here because that goes to I of this thing, and so on. And so on, and this goes here, down here to here, and this is a 1. So in some sense, this is what we call block form. This is a block 0, and this is a block identity. And now let's see what I've got here. T of IE, this is multiplication by I. So T of IE is minus E1, IE1 is minus E1. T of, right, that's multiplication, is minus E1. So it is minus 1 here, and so on. It's an obvious thing. You have minus a thing, and here's some block form. So you check almost immediately that the matrix is 0, identity, minus identity. Right? That is a very important matrix that appears in every part of life. Right? It's very closely related to harmonic oscillator, in fact. So this thing we will call J. If you go into electrical engineering, it's very interesting. Maybe nobody's here from electrical engineering, but instead of writing I for square root of minus 1, they write J, right? It's really funny. Small j, not big J, but this write J. So I always write I, but I always write J for this matrix, all right? And so what we have proven is rather nice, that the defining equation in GLNR for the elements of GLNC, we even proved more than we had to prove, is just that the matrix has to compute, or the operator has to commute with that matrix. So it's a very interesting thing. It has to commute with that matrix. Because it has, there it is. It says T of IV is I T of V. That is a statement that T commutes with multiplication by I. We maybe should write it here. T commutes with multiplication by I. T commutes with multiplication by I. That's the defining characteristic. And so at the matrix level, well, at the operator level, where I call it J, in root GLNR, if you haven't done this, maybe you should do it. I'll give you some hints the way I think about things anyway. So let's write here, GLNC equals the set of T in GLNR, GL2N of course, R, such that if we define J to be the operator of that matrix, or if this is all matrices, such that Tj equals Jt. Right. Another way of saying that condition is that J inverse, this is the commutator, this conjugate equals T. It says that the transformation centralizes the complex structure. Isn't that beautiful? It's a very precise equation. And in fact, since you might be interested in this equation, let's just write it down. Let's write down that T, it's pretty clear that block form is important, so we write down T equals A, B, C, D in block form. Block form. So it says that on the one hand side, JT, so that's in block form, that's what do I have, identity down here? I think identity down here, minus identity here, right? Could be the other way around. I never know. Let's see what that is. That's equal to minus C, minus D, AB. right? That's on the one hand side, and then on the other side, you have A, B, C, D times the commutator. I'm computing out the commutator, but I always like to compute it out like this. So AB, so that's B minus A, D minus C. In block form, so these two things have to be equal. And so that means, let's go through there what that means. That means, that's good enough. So it means A equals D. What else does it mean? You see any good things here? B equals minus C. B equals minus C. That's good. And A equals D. B equals minus C. A equals D. B equals minus C. That's okay. That's it. So in fact, the matrices in the matrix of T is complex linear. It means that this matrix looks like, what did I just say? A, B equals A. What did I just say? And B equals minus C. Where was B? Here. C equals minus B. I like it this way. Okay, that is a defining equation. That's a defining equation. It's a very heavy equation, right? Right. Very special transformations are in GLNC. Okay. So one way of understanding the unitary group is the transformations in the orthogonal group which commute with J. The complex linear transformations which preserve the norm. Right? Which preserve the norm. So that is the equation. In other words, conjugation of this thing T J inverse. By the way, what is J inverse? I hope it's minus 1. What is J inverse? Is it J? J inverse? No, it's I think J inverse is minus J. And it should be I times I inverse, multiplication by I inverse is multiplication by minus I. Right? Okay, so J inverse is minus J. So that's an easy thing to compute here. Okay. So that's equal to J. G. Okay, that's the equation, and that's the unitary group. Now another way of looking at this unitary group is that, well, if you take the standard complex basis, this is the complex basis of Rn, of R2n, so complex basis of Cn, right? Then in fact, T is in the unitary group, if and only if its matrix is what it has to be, matrix of T. Well, it has, these things are, that's an orthonormal basis in the unitary, in a complex basis, right? It's an orthonormal complex basis. Some people, including me, call this a unitary basis. It's orthonormal with respect to the inner product, but it's a complex base. Yes. So and what is the matrix? Well, we talked about this before. It's rather boring. I'm sorry I'm boring you. You have to put T of 1 here. You have to put T of 2, E2 here. And you have to put T of En here. Right? And of course, if you start out with unitary basis, you have to get a unitary basis. So that says that the norm of this thing, T of 1 squared, equals, all these norms are 1. And they are perpendicular with respect to the standard for I not equal to j, with respect to the standard inner product. Okay. So that's what the unitary group is. Unitary group stabilizes the standard structure. Any questions? I don't think so, maybe. It's a little very tough for you all to have all these lectures in the late afternoon. I'm trying to get some elementary stuff. Okay. So that is your second compact group. Why is it compact? I mean, maybe you're going to ask this question. It's a reasonable question. It is, so let me just write the answer to that question. Why is it compact? Well, recall the orthogonal group is compact because we can embed it in a sphere and all this stuff. The orthogonal group is compact. So the unitary group is a subset of the orthogonal group. Right? And the orthogonal group is compact. Yeah, orthogonal group is compact, we talked about it. And the unitary group is defined as a set of T in the orthogonal group which commute with J. That's a precise definition. That is an equation of the unitary group. That is an exact equation of the unitary group. So this is, if you like, this is the equation, and it's a wonderful equation. It's even algebraic. We can look at it. We can look at what it is. It's a wonderful equation. In particular, it's continuous. So this equation is defining equation is more than continuous. It's better than a continuous defining equation. Much better. It's beautiful. It's simple-minded equation, and therefore this thing is closed. I hope you know a closed set is defined as a zero set or a level set of a continuous function. Do you know that theorem? It's called Ticci extension. There are various. Under reasonable conditions, given a closed set, it is the level set or the zero set of a continuous function. That's almost the definition of closed set. You need a little bit about this topology business. I don't know what you need. Somebody, probably you know what you need.
I think
Maybe again T4.
yeah.
Something close to, I don't know, more than Hausdorff maybe. Because you need, I think, yeah. So level is a closed set. So the statement is, this is a closed subset of the orthogonal group, and a closed subset of a compact set is compact. That answers your question. And if you haven't ever answered that question before, just try it. Write down a sequence of points and try it. It's completely clear. Okay? So a closed subset of a compact set is compact. So that says it is compact. So the first two wonderful classical compact groups you've seen are the orthogonal groups, which, because he asked me about, has a submanifold and so on. You see, it's not connected, right? There's orthogonal groups and unitary groups, and the unitary groups will be connected. So that's and of course, when you look at this, when I told you we would be very happy probably to look at the SON, that means determinant 1 and preserving area, and SUN, that means determining one and preserving area. That means in matrix level or operator level, this determinant is 1.
UN is connected?
Hmm?
UN is connected?
UN is connected. Let me tell you, he was amazed that UN is connected. Maybe he doesn't even believe it. Let me tell you why psychologically UN is connected. Okay? The unit sphere in the real numbers don't forget what the unit sphere in the real numbers is. I'll write it down. This is a set of X in R. So the norm, okay, I'll even write square equal 1. That's norm equal 1. The unit sphere, as you see, is plus minus 1. Right? So the unit sphere in the real numbers is not connected. Okay? The unit sphere in the complex numbers is the set of Z in C such that the norm of Z equals 1, and this is the unit circle. And this is connected, and that's the point that's going on all the time here, is this thing with the unit spheres. Okay? Okay. So those are the first two you understand. And it's very interesting, that's what Nicholas was reminding me of, because I'm a complex analyst. Yeah? You have S2N, this is a very interesting thing, is a homogeneous space of the orthogonal group 2N. When we regard it, S2N minus 1 is regarded in R2N. But the same argument that I made this morning, S2N minus 1 is a homogeneous space of UN. It's the same argument, orthogonal bases, all these stuff, when S2N minus 1 is regarded in CN. So this is a very interesting example of, you have the same manifold n, which is S2n minus 1, but with two groups that are very important, O2n and O and UN acting transitively. So that's an interesting remark. You can regard it as a homogeneous space of the ON, or the homogeneous space of UN. You talk to your physics friends, almost always they will be talking about UN. I think it's fair to say. And that was Wigner's point. Eugene Wigner, the great physicist, could not understand how mathematicians discovered things like this. Of course, they're immensely important in physics, but mathematicians understood spheres, looked at the geometry and understood inner products. I will a lecture today, I don't know, early perhaps, I'm not sure. Well, maybe not, I don't know. By the third classical group of great importance. It is called the symplectic group. Group is defined, it exists primarily because it's stabilizing some structure, and quite often, I would say I'd like to emphasize, quite often it is defined by an equation of this type. Let me emphasize the equation of that type is an involution. So these groups quite often, for example, here the unitary group or the complex linear group is defined by an involution, namely that operator J. Why is it called an involution? Yes. Notice that J squared, J, T, I think it's an involution, let's look out here. Let's apply this thing twice. Yeah, I'm lucky. This, I apply it once, and I apply it again. All right? Right? I want to see what happens if I apply it twice. Okay? So that's J squared, J times J is minus the identity, times T. J inverse times J inverse is minus the identity. This is equal to the identity, T identity, which is equal to T. So you see, you apply it twice and you don't do anything. That's what we call an involution. So let me just say this, GLNC is defined in GLNR by the above involution. So just keep that in mind. Involutions are extremely important in defining these groups. This is a fixed point set of an involution. GLNC is the fixed point set of an involution. Of the involution. Which is given by T, that's mapped to J, T, J inverse T. Very important remark, so keep it in mind as a fixed point set of this. Well, let me even say on GLN 2NR. And correspondingly for the orthogonal group. So now let us go to the symplectic group. The final symplectic group, which I'm going to denote by SP2N, C, containing, this will play the role of GLNC, containing what we're calling the unitary symplectic group U, SP2N, SP2N. I'm dealing with compact groups, and you see, we were originally dealing with GLNC with all the general linear transformation, and now instead of having GLNC, we're going to have a very important group which is called the symplectic group. It's inside of SP2N. So this is an introduction to the symplectic group, SP2NC, the complex projective group. Okay. Now, as physicists will tell you, particularly Professor Shu, the fundamental space for many physical considerations is a vector space V plus its dual. Okay? This is a fundamental space for many physical considerations. This is somehow the fundamental space of symplectic geometry, and it will be the fundamental space of this symplectic group. So here I have V, everything finite dimensional, is a complex vector space. Vector space. And V star equals its dual space. Okay. This is an amazing thing. This space comes equipped with canonical symmetric and alternating, and now let's just say anti-symmetric form. Now, let me review for you, since you only had such considerations in Mickey Mouse linear algebra, what we are talking about here. What does it mean, a symmetric form? So, a symmetric form is, first of all, B is a bilinear form. What does that mean on a vector space? It means B is linear in both arguments. That means if you put A plus VW and so on here, it comes out, it means the same thing in here. Linear in both arguments over the field in question. Symmetric means the obvious thing. B of VW equals B of WV. As almost no, it looks very harmless. And as an example, you take the standard inner product. This is V1, W1, so on. This is the standard inner product on Rn or Cn, whatever you want. This is symmetric. That means symmetric. Alternating or antilinear means B of VW equals minus B of WV. Yes.
Is antilinear then the same as antisymmetric?
Yeah, what did I just say? You're so nice, Mr. Wright. Antisymmetric, yes. It's antisymmetric. Antilinear would mean if you have I inside, it comes out to minus I outside, right? That's anti-complex linear, I'm sorry. Thank you very much. So antisymmetric means that. Yeah? Okay. Now, you have heard of this thing before. You didn't know it. Because if you have in R2, you take two vectors, V and W, maybe they look like that, and you form the matrix of these two vectors, and after you form the matrix of these two vectors, you write in and make the determinant. Right? And now let's say V is it, let's say this is the determinant, this is the area. A, B, C, D. This is the area. Now if you exchange, everybody's optimistic, you exchange the D and W, it looks like this, A, B, C, D, and so on, and you take the determinant. Well, what happens? I hope you see the determinant here was AD minus BC, it's here now BC minus AD, and that's the standard factor determinant. You make that kind of exchange, there's a sign that comes out here, and in this case it's minus. Now what in the devil could that mean in my previous discussion calling this area? I called it area, the determinant is area. The determinant is area in the sense of orientation. If you have V as the first vector and W as the second vector, and you make this parallelogram, and it's positively oriented from V to W, yes, you got a positive determinant. If it's negatively oriented, you get a negative determinant. So area has a sign. Angle has a sign. Depending on the orientation of the angle, that's the orientation going around S1 or going the other way around it. So keep in mind, everything has a sign. It's hard to believe, but area has a sign. It can be negative. Right? In some sense, maybe you're looking on the other side. Right? Something like that. Think of Rubik's bands and so on. So area has a sign, and so determinant is an alternating thing. Determinant is an alternating thing. And in case you haven't thought about it before, if you take a determinant of a bunch of things, and you're crazy enough to move the order around with a permutation, which we talked about. So that changes the order around. So you're making this parallelogram, and you're changing the order. It's the same parallelogram somehow, but it's ordered in a different way. Of course, this is equal to -1 to the sign of the permutation. You have to remember what that really is, the sign of the permutation. -1 to the, well, it's the sign of sigma times the determinant of the original thing. You have to remember what the sign of a permutation is. Permutation is either even or odd, depending on how many involutions you have in the permutation. Right. So determinant really is an oriented thing, and if you mess around with it by taking a permutation, you will change the orientation and get a minus sign. Okay. So we've already seen bilinear forms which are antisymmetric. Namely, they look very much like determinants, right? Because area is signed area, if you think of it correctly, is a multilinear form. Okay, so that's the simplest example that you can think of an alternating form. And I said the fundamental vector space for physics, for a lot of physics, and particularly nowadays for Professor Xu, and maybe even in your thesis, I don't know, is V plus V star. Certainly is an important vector space. V plus its dual. Dual means the space of linear functions on the vector space. And now let's have some fun and define the symmetric form on that thing. So the symmetric form I am going up to call the symmetric form on V plus V star. So remember, V is, let's say here V is, it could be a complex or a real vector space, say vector space, over something you like. I like the complex numbers. And V star is the dual space. Remember what dual space means. F is in the dual space, means F is a linear function, which some people call functional, linear function on V. So V in the space of linear functions. Okay? Now watch. I'm going to define, if I take some element here, elements of here, I will write V for vectors, and I will write phi for functions. Maybe I will write F for function, F for functions. So I will write VF as a point in this space. Okay, that's a vector in that space. Okay, and now the symmetric form is this. Symmetric form applied to VF, comma, V prime, F prime, equals, I mean, this is just other things, is equals, you apply F prime to V, and you add to it F of V prime. Vector, function, vector, function. Well, I'm writing down a symmetric bilinear form on this space. I apply F prime, the function, to the function in the second argument to the first vector, plus the function in the first argument to the second vector. That is obviously symmetric. You can check it. It's symmetric. It's a fundamental symmetric, non-degenerate bilinear form. This is canonical. God gave this to us. Canon means God. Yes, yes. Well, it means this. I didn't have to put anything into this. There it is. Okay? And then, if you look at this thing, A, there's an alternating form. Well, it's not very hard to imagine how you get an alternating form. You just mess around with a sign. Well, it's F prime V minus F V prime. Yeah? That is a God-given, canonical, alternating, you check if it alternates. If you exchange, look, I mean, it's completely clear. If you exchange that guy for that, you get the opposite sign. These two things are canonical, symmetric, and alternating forms. Okay? Okay. So that is very interesting. We have found an alternating form appearing in life. And now I will define the symplectic group. This group, the complex symplectic group, appears in life because of this form, A. And it appears in all over geometric physics nowadays because of this form, A. A little bit advanced. One of the main theorems is using this. Well, I won't say anything. This is of central importance in many considerations in modern mathematics. So I've defined it for you. Let's see if we can write down something in a basis. So, well, first of all, before we write it down, let's say that SP, the symplectic group, let's say everything over C. So let's make these vector spaces over C. C vector space. SPC related to this alternating form of above. So that is the group of transformations T and GL of GLC of this space, V plus V dual. My friends in physics call this space W quite often, so we'll all call it W, such that A alternating T of a point, C, T of eta equals A of T and eta. Every group is defined because it stabilizes something that should be symmetric. The structure here is this alternating structure. It is related to all sorts of things in life, in particular area and so on. Yes? Let me just make a remark about physics. Physics people, do I see many here? Let's see, 1, 2, there are a few physics people here still. I haven't destroyed them all yet. Yes. People will say, and if you will read in Arnold, if you have a Hamiltonian system, Hamiltonian preserves some sort of symplectic structure like this, the physics people will tell you area is preserved. It says if you have a Hamiltonian system, that is the system of classical mechanics, and you move around in space, it means that area, for example, if you have a rectangle here, you may move it like this, but area is preserved. Not just the it's not an isometry of the rectangle as you move around, but the area of the rectangle is preserved. Area is a constant of motion in a symplectic flow, right? You agree? Yes. And very nice to read Arnold in this setting. So anyway, this is it says A should be preserved. And now maybe we should have some fun. It's very tiring, this lecture for you. I'm apologizing. Let's see if we can do something. Okay? Let's see here. If we have E1 through En is the basis of V. Try to write down what these symplectic operators really look like in matrices. This may be the standard basis of V. And then, because we're going to the dual space, we have F1 through Fn is the basis of the dual space. That is called the dual basis. And it means that these functions do the right things on this basis. It means Fi applied to Ej is just either 1 or 0, depending on what it is. So if you have a base, you have V and V star, so you have the basis of V plus V star, you take the first things, E1 through En, and now there's a big question, by the way, if you look in various literature things, where you put F1 through Fn. Some people, we will see, maybe we will make it nice, but I will tell you, I work in this area, and maybe the right thing to do is, maybe, we'll see at the end, maybe we should write, it's a question of how the matrices are going to look, should write, instead of that, E1 through En. I mean, it's a question of how you want to write it, and maybe Fn to F1. I'm not sure. You see, it's a question where you put the basis. I mean, you pay your money and take your choice. Life is capitalistic. It's a question what it brings. As my American friends say, what's it good for? Yeah. So it's a question of, it's a question of what it brings. And maybe the order here is better here. Let's start out with that. See what happens. Okay. Okay. terrible. The D-Pack, I thought you were gonna steal an eraser over there.
I forgot.
What are you worth? You didn't steal this eraser. This,
Yeah, I forgot. I'll do that.
yeah. This, you hear this noise? This noise is dedicated to D-Pack. Terrible noise. Let's see what happens. Let's try to write a matrix down here, if we can. So let's try. So let's say V is equal to A I E I plus B I F I. Oh, that's, so, yeah, I mean, maybe, let's call this C. So it is a combination of elements of the vector space V and with the dual space C. And now eta, say, is CJ EJ. I hope I can get away with doing this. VJ, no, DJ FJ. It's great to have physics in the audience because they calculate really well, so that you can do this calculator in your head. I have to do it, and I'll probably make a mistake. But we have Mr. Weiss here, you will find my mistake. You usually do. So let's write it down, okay? So let's write it down. A of C eta is equal to, let me write it very slowly, we're all getting tired and we might as well just be, you understand when I write I here, I mean sums. Because we get very tired writing sums. I think we won't make a mistake by, this is A EI plus B I FI. Oh, I can already see I think I'm in very big trouble. So I think I'm going to write K here. I'm sorry, J here. J here, and I'll write K here. It's always better to have too much notation and write L here. I hope that helps. So AIEI, BJFJ, and now I get to write CKEK plus DL FL. Okay. And now I have to write it down what that is. Well, I take the vector in the first place and hit it with the function in the second place. You see, I get very physical with this. You take a vector in the first place and hit it with a function in the second place. Right? So that means I take a vector in the first place, like the first one, E1, and hit it with a function in the second place. Now the function F1 gives you something, but the rest of them give you nothing. And then I keep doing that, and then I have E2, and then F2 gives you something, E3, F3 gives you something, and so on. So my claim is, the first part of this anyway, is AI, DI, DI. Right? Right? And now what I have to do is to take a vector in the second place and hit it with a function in the first place, but I have the other side. It's looking very much like a determinant. I was very lucky with my notion of what a determinant there is, very extremely lucky. So this is B, I don't know, maybe I'll be careful and write this, it doesn't matter maybe, but I'm going to write this as B, J, CJ. Did I get this right, everybody? Right on. Right on. I think it's true. Right. So, what this is what I'd like to do is write this as C transpose, so the standard inner product times something in the middle times eta. That's the way all bilinear forms should be written. C transpose blah eta. And you have to determine what the blah is. So what we have here is let's see here, what is C? Where's the double C? There. So we have A1 through AN, and then B1 through BN, times some blah. And now I have to write the same stuff down here, so this will be eta. Eta is C1 Cn times D1 Dn. Right? And now, let's see if we can get this blah right. What we have to do is we want to get so we want to get A times D, and so what I claim we want to do is we want to make this blah, so what we have to do is we have to make this thing, that we put the D's up on the top, D1 through Dn, and the C's down on the bottom, because that's what we got here, where to go, there, and we're going to have AD. We want to, AD is going to be bilinear there in that good way, and the C's on the bottom. That's great. So this operator here has to take the D's up here and the C's to put them down there. Okay, let's try it. So let's try this operator. What's the operator that does that? Let's see here. Maybe, does this put the D's up there? Huh?
I mean, the second column should be identity 0, and the first column is 0 minus identity.
Yeah, you're even thinking ahead. You're much faster than I am. But I want to just put the D's up here, first of all.
Also, it's 0 identity.
So in block form, this will be 0, and this will be the identity. I'm going to worry about the sign later. Okay? And that brings D1 up, and this brings D2 up, and so on, right?
Yeah, I mean, this brings
Huh?
C down. But
What?
I mean, the first column brings C down. I guess it doesn't matter. And then you write the second.
Oh, let's see here.
But it's the same if you write the second column.
Row. Oh, I see what you're saying. Row times column.
Yeah, but you need it anyways.
Well, wait a minute, I want to bring D1 up, so I should write it here. That's what you're saying. Right? So I bring D1 up, and that brings all the D's up, right? And let's see here. I want to bring the C's down. I hope that what I'm going to do here, and what you just said, I should put minus identity, right? Because I have the... Okay. That's a famous matrix. The inner product is, the blah is J. Isn't the blah my J matrix that I just said before? Or at least up to sign is J. right? I think it's even the J that I had with the minus sign down here. It doesn't matter too much, right? I think it's just a question of some orientation. So we say, very interesting, that the symplectic form A, the alternating form A of C eta is equal to C transpose J eta. This J keeps appearing in life somehow. Very interesting, right? Very interesting. For those of you who are interested, J in this case is somehow related to quaternions. So that's J. And now let's see, a transformation is symplectic if A T C T eta equals A C eta. If and only if it commutes with J. So that says that A, that means as a matrix, T transpose J, T, that's T equals J. Right? Because this thing here, if you're writing what it is, this is T transpose, it's C transpose, T transpose JT eta, and this thing here is just C, it has to equal this, and so that says this part, with J of course, J eta, it says that. Okay? So the involution in this case is a little bit complicated, right? It's not just commuting with J, right? Because you have a big transpose in there. That's not just commuting with J. So the complex symplectic group, SP of the vector space V, equipped SPC of the vector space V, let me even write a bunch of notation, equipped with the alternating form A. We call that form the canonical symplectic form. Let's call this W for the V plus, equipped with a canonical alternating form, which in a basis we write as SP2NC, because it's 2n-dimensional and it's complex bilinear. It's complex linear. Is a set of operators, or in matrix language if you wish, such that that T, it's a terrible thing. Let me move this on the other side. So let's see, I move it on the other side, I get JT equals T, and Professor Penkoff hates me when I watch this, so I write, in order to make Professor Penkoff mad, I write minus T for minus inverse transpose. He gets mad at me for that, but minus inverse transpose. Okay, so that's I put it on the other side. I had transpose, put the inverse transpose here, and then JT inverse transpose J, and now T is equal to I have to hit this with J inverse on both sides, so J inverse minus JT transpose. And actually I can move, it doesn't matter because J inverse is minus J and I can move this around, and I much prefer to have it with a conjugation in a good way. That is the involution. You see, it's an involution. Do it twice. Have fun and do it twice. Which defines the complex symplectic group on the canonical vector space W, which is the direct sum of V and V1. This is the involution that defines it. And now I have run out of time, and you run out of patience and energy. Tomorrow I will tell you that the compact symplectic group, the compact group behind this, what this is this group, the set of transformations in this group, just like we've had before, in this complex symplectic group, which are unitary. Okay? So the intersection of this group with the unitary group, whatever that means, I'm going to be precise about it in a minute, you're dead tired. But look what's happening. The first structure that needs to be preserved is this alternating structure that is fundamental in physics, namely the canonical all-Lane problem. But then secondarily, we need to preserve the unitary structure. So you need to preserve the norm and the symplectic structure. That is called the compact symplectic group. It's compact, and it's written as USP true N. Okay? The unitary symplectic group. We'll talk about it in detail tomorrow, a little bit. But I hope you have seen, you have the groups ON, you have the group UN, you have the group USPN, and these are three compact classical groups, and this is what Hermann Weyl called the classical groups. And these things are given for every n. So one refers to them as the infinite series of orthogonal groups, the infinite series of unitary groups, the infinite series of unitary symplectic groups. These are the only compact groups, effectively, which have an infinite series. You can take products and do all sorts of stuff, but yes.
Still, we would say that they only exist, so the unitary symplectic group only exists then for even.
Yes, that's absolutely right. That's the reason, that's my private notation, and many people will like that notation. But obviously you need even because, so W equals V plus V star. Let me just say what this is. And the dimension of W is 2n, which is the dimension of, and n is the dimension of the base vector space. That's a little bit confusing. And that's a question of authors. Some authors may write an n and not a 2n. And I really almost insist on 2n. Okay, I don't know what you physics people say, I don't know. Do you give it a name? USP2? You don't give it any name. You don't give it any name.
Usually in literature they are asking the original SP to NC is written SP to NC, but the compact one is written as SPN, not even U.
Okay, so let me just because there's a very confusing thing going on here. If you write just SPN or something, you may have done this entire thing over the reals. Okay, the real symplectic group is defined over a real vector space. So V plus V star is a real vector space. That is the real symplectic group. This is in modern dynamical systems physics and Gromov theory and all this wonderful stuff, the group that is playing a role at first is the real symplectic group. Okay? And that means you take the vector space V over the real numbers. I took it over the complex numbers because I wanted to have the unitary symplectic group, if you like, its maximal compact subgroup. Yeah.
Is the symplectic group also compact? Or probably should be?
Well, you can answer the question yourself. It's a set of T in the complex symplectic group, which are unitary.
No, I mean the symplectic group itself. It should also be compact.
You mean the SP?
Yes.
No, definitely no. No, let me just, he asked, is it compact? And let me just say why it's not. Here's the defining equation, right? That is a defining equation of complex matrices. So that is a defining algebraic polynomial equation in some vector space. So it is really an affine variety sitting in some vector space, affine manifold sitting in some vector space. It's very interesting. It's sort of a non-trivial one, right? I mean, because you have this transpose and all of this stuff. Okay, inverse transpose. right? Okay, so you can write it down and you will see its equations and you will see it sitting in a vector space of matrices, complex vector space. So as you know by the maximum principle, it can't possibly be compact, okay? Because it's a complex equation. It's a holomorphic equation, it's a complex algebraic geometric equation. But inside that, you have the unitary transformations. So in addition to preserving the alternating form of physics, you want to have it preserve the unitary form of physics, right? And that is the additional unitary symplectic group. And he was pressing me on this. Again, there are 3 infinite series of classical compact groups you're looking right now. All other things are either constructed from a torus, or which is easy to understand, or a product of various things. Yeah. And that is not difficult to prove, but it is the first basic theorem in what we call compact classic groups, or Lie groups of compact time. Okay. This is where it started in the early part of the 20th century with Hermann Weyl. Okay. Thank you very much.